In this video I'm looking at the close range noise of 10 MHz oscillators, and I will start with this one from Wenzel Associates. Sometimes the oscillators, the local oscillators of my system are unstable. This happened here. The noise bursts were in channel 1. And I'm waiting for one more to happen, but I cannot control this. It is just a random event, and it is in the crystals. Now, since it happens in only one of the oscillators, it doesn't affect the result that I see on the correlation screen much. I should be able to see it if I look at the subscreens here and here, amplitude, and this one is phase. If I look at much fewer averages, I will get only the latest ones, and as you see, they are lower. So on these 300 it made a difference of 2 dB or 3 on the phase. And here is the amplitude, and I go back to include many. And then it's the other way around. And if I go for the phase noise, this is 500 spectra, and now I look at the latest 50. So oscillators are unstable. That is part of the phase and amplitude modulation that I have of the system. And as long as it's not correlated, it just makes the time I have to wait for a stable correlation spectrum longer. Now I had a series of events again. So I will knock on the oscillator, channel 1, to vibrate the crystals, and that could change this situation. Knocking on the box caused the frequency to jump by about 15 Hertz. They don't lock anymore to each other, the oscillators. I have to tune a little bit. Here is the signal analyzer window of Linrad. After 39 minutes of collecting correlation averages. The curves here, the yellow is phase noise, the sum of the real and the imaginary powers. This yellow curve is phase noise, and the white curve here is amplitude noise. And I think colors become more visible when I move the camera. And I don't know why that is, but anyway, I will save this to a disk file so I can look at it with a pixel editor. I can click on this box here to get a different display mode. This is much more informative. It's phase noise only. The yellow curve shows the size of the real part when it is positive. Means it is correlation noise from the signal source. Blue is when that real part is negative, and that happens on the spurs. This first one is 50 Hz, this is 100 Hz. The red dots here is the imaginary part, and that should be only noise. It is totally uncorrelated, and if I wait it would go further down to some level I don't know, but I didn't have the patience to find out. The red track is the power of the phase modulation in channel 2, while the green trace is the phase modulation in channel 1. And it's very obvious that phase modulation is much stronger in the in channel 2. You can see the red dots go all the way up here, while the green dots, they go also very high. But here the red dots go much higher than the green dots. But here there is some spur which is not an overtone of mains, and that is stronger in channel 1. It's pretty clear that the local oscillator of channel 2 is much better than the one in channel 1. You can see the phase noise differs by about 6 decibels at 50 Hz. I click once more here to come to the amplitude noise. And it's the same. Channel 1 has a lower amplitude noise than channel 2. But the amplitude noise is not so high, while the amplitude noise of the signal source is fairly strong. So here I have a very good evaluation of where the noise level is. The imaginary part is all the way down here. So when I click the main curve here, the white trace doesn't change, because adding something that is more than 10 decibel weaker doesn't make any difference. The yellow curve, however, is a little bit different, and I will save this also, and also the amplitude curve, to look at them better in a pixel editor. Here is the midpoint between 0 and 50 Hz. So that's 25 Hz, and I can read this as minus 149. And I get the information from the coordinates up in the corner here. And it's quite easy to see 157 at the 50 Hz spur, 162 at the 100 Hz spur here, and 150 Hz, that's minus 164, and so on. This is a measurement made with the FSWP on the same oscillator. The data point I just arrived at are those that you can see I have marked crosses with some blue color in them. They are the phase noise, and the phase noise is the blue curve, and they come very close to it. The red lines through or just a little bit below the phase noise measurements are my amplitude noise measurements. They are significantly below the amplitude noise from this measurement. Although very close, the amplitude noise is low, but in this range it is significantly higher than the phase noise. And the reason might well be that the power supply was not properly filtered when this measurement was made. Now I will be looking at the noise from another oscillator from Wenzel Associates. This is a modern one. The other one was 20 years old or so. Here is the average correlation spectrum after 6.5 hours. A little bit more. White is amplitude and yellow is phase noise. And I press G and save this to look at it later, perhaps. And then I click here again to get to the phase noise screen. And here we can see that up to this point data is reasonably valid. Maybe from here, that's 25 Hertz. At closer range, the red dots are equally strong as the points of the yellow curve, and that means that the random noise from the receive system is equally strong or stronger than the noise from the oscillator. So with my system I cannot come closer than about 25 Hertz on this oscillator with respect to phase noise. And of course I save this one also. And look at the AM noise. And amplitude noise, I can go a little bit closer here. And it is very low compared to what I have seen before. And that's interesting to me because it opens possibilities to investigate amplifiers by use of this, investigating amplitude noise of amplifiers. And of course save this also. And I will measure the values of the amplitude and phase noise from these graphs. Now I'm looking at this oscillator. It gives about 1 watt. It has 20 crystals in parallel and it's my own odd design. It's attenuated by 16 dB, first 3 dB here and then 13 more dB from this attenuator. Here is the signal analyzer graph after 1 hour and 38 minutes, 10,700 averages. And when I move here you can see that the yellow track is much lower than the white. Phase noise is much lower than amplitude noise. But the phase noise at 50 Hertz is fairly strong, minus 153, and it goes rapidly upwards here. But I shift now to the other display kinds. Here is the phase noise information, and we can see that the random noise from my receive system is well below the phase noise of the unit I'm testing. So this curve is correct all the way up to 10 Hertz or something. And I can read this out. But first I will look at the AM noise here. And it looks a little bit different. I will change here to 130. So I can read closer in frequency. I have changed the scale parameters for 5 dB per division and starting at -60. I set those things here. And then I save 3 more images, so look for the details in this region with the pixel editor. I have this connected, this attenuator and this one. And instead I have set this attenuator to 16 dB to see if I can see any difference. The result is unexpected. This is what I am currently collecting. It's now 1 hour and 54 minutes, 12,000 averages. And here is the curve. And now I look at the image I saved with the other attenuator. And you can see here the phase noise is a little higher. A small difference, but it's there. The amplitude noise is not very different. If I go close like this, and then I go back to what I'm just currently collecting. So it's lower by maybe 1 dB. And the difference is bigger at very close frequencies. So this is the old data, and here is the new. It's a little bit difficult to maneuver on the screen. So I find it surprising. I had expected the amplitude noise perhaps to change a little, but they didn't expect a visible change on the phase noise. On wider frequency separations it's different. Here is, well, it's 200 Hertz. We don't see the scale because I moved it for the image to have come on the same position, the old saved one. Here is the old, and that's the new. The difference is small. So at very close range I can see noise from the attenuator and phase noise. Well, I have enabled the internal generator just to show to myself and also to you looking to this that the amplitude spectrum, the power spectrum of the demodulated phase noise is flat. And of course correlated is very low, there is no correlation, these are random numbers. But this is the demodulated phase noise. And here is the demodulated amplitude noise. It goes down a little bit here and then up here. There is some artifact in how filters are applied. There is a filter going down and there is a correction added, and there seems to be an error of half a dB or something. And this was done for completely different purposes some time long ago, so I don't want to spend time trying to correct it. The precision is not going to be better than a bit dB anyway for this kind of measurements. It takes about 1.5 hours to collect many enough spectra to get a good estimate for the sideband noise of this oscillator. I can select a smaller transform. I go for 12 here on N. It was 12. I changed that to 10. Now it will run 4 times faster. And you see, it rapidly steps up several transforms at a time, and I can fairly quickly see what goes on. But it's difficult now to see what is a spur and what is really the noise. But I can see here, here is 200 Hertz, so 150 Hertz. I read minus 161 and 164.5 or so for the phase noise. And of course I can go the other way around, and I put 14 here. Now it's going to be very slow. But I will see much better at close range. I actually didn't do this before, so we will see. Maybe here is the first. And they come one by one now, the transforms. And to have an idea how long I will have to wait, I click in this box, and you see the noise of the channels here and here, and I will have to wait because the random noise, the red dots, are at approximately the same level as the yellow and the blue, and there are similar amounts of yellow and blue points, means there is not much of the correlation signal. This is just random noise, and I have to wait for that to even out. And maybe I would have to wait for 6 hours or even more, because at very close range the signal to noise ratio of the system degrades because of the phase noise of my local oscillators. For amplitude noise, it is a little bit better. It seems that I already have reasonably accurate information here. This is the GIF file I just saved. I'm using the GNU image manipulation program, GIMP, and I will use that to evaluate the pixels on the yellow curve. I can find the x coordinate for 0 Hertz here, and then read it as 988 pixels, and then I put the cursor on 100 Hertz, and that's 1261 here. So I find 1261 minus 988, that's 273 pixels per hertz. So I can find the x coordinate for frequencies 10, 20 and 50 hertz, like this. So I add the DC component 988 to these differences, and here are the coordinates. So this is 1015, and I read that as minus 131. And of course the curve is a little bit up and down, so I cannot do this very accurately, but this is an estimate I can do. 1043, that's here, that's 20 hertz, 142 and a half. Now here is what I found. The frequency scale from 10 hertz, 100 hertz, 250 hertz logarithmic. The modern Wenzel 501 25 420, it is good at close range, but it flattens out a little bit higher than the older Wenzel. It starts with a little bit more noise, but it steeps faster. And it goes further down. And here is my homemade thing. I went closer with measurement for it, but it goes like this, and I know from other measurements that it goes far below the Wenzel oscillators at very wide frequency separations. Now, the interesting thing of this little study is that the boxes, they are AM noise, and here the difference between my unit and the modern Wenzel is about 10 dB. It means I can use this very good oscillator in terms of amplitude noise to send a signal into this my own homemade oscillator, which I can use as an amplifier to see how much noise it adds depending on the power level, and I can also inject the signal from the good Wenzel into different stages of that amplifier to see where the noise is added and perhaps understand the mechanism. Is it amplifiers that add noise? Are the voltages not well enough filtered, or is there some other reason to add amplitude modulation in amplifiers? This will be the next video, hopefully, if I find something of interest.